Hi. So good afternoon, everyone, and a warm welcome to all to this LaserTalk 25. I am Tanveer Ahmed, and on behalf of Laser Science Services India Private Limited, it is my pleasure to host today's technical webinar. I would like to thank you all for taking time to join us, and we are very delighted to have researchers, scientists, engineers, academicians, and industry professionals from across the country with us today. Today's session focuses on an exciting and rapidly advancing field, light sources for Coherent Raman and Multiphoton Microscopy and Ultrafast Spectroscopy. We'll be focusing on Coherent Raman applications. And before I begin, I would like to request a few quick notes. I would request everyone to please keep your microphones muted throughout the session. And we will take your questions and answers and at the end of the talk. And for that, please write in the chat box for any question you have, and the speaker will take it one by one at the end of the talk. Now, it is my privilege to introduce today's distinguished speaker, Dr. Ingo Rimke, who is currently Chief Technology Officer at APE Berlin. So we will have a brief overview of APE Berlin. Maybe Professor Dr. Rimke will give us towards the end of his talk. And Dr. Ingo Rimke is Chief Technology Officer at APE. I'm honored to welcome him to this LaserTalk 25. Dr. Rimke holds a PhD in physics and joined APE in 2001 as an R&D engineer, specializing in nonlinear optics with a particular focus on optical parametric oscillators. Over the past 2 decades, he has played a significant role in the development of advanced light sources for Coherent Raman Microscopy, contributing to innovations that support cutting-edge imaging and spectroscopy applications worldwide. Today, as Chief Technology Officer, Dr. Rimke continues to lead technological advancements and drive innovations at APE. We are delighted to have him share his experience and expertise with us today. Dr. Rimke, thank you very much for being with us today. And now it is over to you.
Okay, thank you, Tanveer, for the very nice introduction. And thank you all for joining this afternoon. I will guide you a bit through this session, and hopefully I will be able to answer all your questions. So what will I talk about? First of all, I just want to introduce the company APE to you. I want to talk then a bit more general about tunable light sources we built. And finally, my focus will be on Coherent Raman Microscopy with our newest development, the picoemerald FT. Okay, APE. We are manufacturing devices for characterization and modification of ultra-short laser pulses. So everything with femtosecond, picosecond, that's what we do. We are serving the industrial and the research market around the world. This is very specific what we do, so it's very important. Whether you are now, I'm talking now to you in India, but I'm also talking to China, Europe, US, basically. This is very important. I think everyone within the scientific community knows how important it is to have that community worldwide, and we very much appreciate that. So the company is already 34 years old. It was founded by these gentlemen you can see here. And so our very first product was the autocorrelator in '93, which still autocorrelator is what many people associate APE with. But already 1 year later, we just bought the first optic parametric oscillator on the market. And that again is a very big milestone. Both product lines are basically the key of the company. Then, well, as it developed the first picoemerald, that was the first fully integrated Coherent Raman light source we had in 2009, and in 2025, the Pico Emerald FT I will talk later about. We are based in Berlin. That is the capital of Germany. And yeah, we are 65 people in Berlin. Basically all R&D and production is happening here. We are having 17 R&D and production laboratories, including 3 clean rooms. The R&D expenditure is 30% of the total revenue, so that's pretty high. But that is really because, well, we are serving the scientific market. I think that's absolutely necessary to do so. So what we are most known for are our laser diagnostics. These are mainly autocorrelators. There are more than 300 autocorrelators sold every year. We're the first address for pulsed picosecond, femtosecond optic parametric oscillators. There are more than 1,000 OPOs in all kinds of varieties in the field. And we like to do customization. We also do OEM for several things. So as already mentioned, we are serving the scientific market, which is very, very important for us, but also the industry. We are a trusted OEM partner for several companies like Coherent, Spectra Physics, Amplitude, Leica, NKT Photonics, BD, and so on. So the product groups we do. I already mentioned the pulse diagnostics, which is basically measuring and characterization of femtosecond, picosecond pulses. We do wavelength conversion, well, starting from a standard laser, 1 micron, Thai sapphire, or you name it, and basically go through the whole spectrum from UV to mid-infrared. And then we can manipulate these pulses with pulse picking, modulation, amplitude modulation, and so on. So just only very quickly the pulse diagnostics, because I'm not going to mention them later on. So we have a full range of pulse diagnostics we can offer. These are, well, as already mentioned, mainly the autocorrelators, but we also can do phase resolved measurements for more detailed analysis of pulses. But also we have a spectrometer, we have pulse monitors. But so coming to the second part of my talk is, well, tunable light sources and systems. As already mentioned, we can do from ultraviolet to mid-infrared. We do femto or picosecond, and this is all multi-megahertz. Typically something like 40 megahertz, 80 megahertz, but others are possible too. This is all in the nanojoule pulse energy range, so it's not high energy, but high average power. So what are these tunable light sources for? Basically, they're extending the wavelength range of mode-locked lasers. Well, you have, well, only a few tunable mode-locked lasers, which is basically the titanium sapphire. Everything else needs some kind of nonlinear frequency conversion. And this is our specialty. So basically, we are sitting behind our systems behind titanium sapphire lasers, ytterbium lasers, so everything around 1 micron. And of course, well, a second harmonic of 1 micron, which is typically 515 nanometers. They're all fully automated and fully flexible. Basically, when you talk to us or to Laser Science, we basically help you to set up these systems, which wavelengths you really need. So, and as you already can see in this sheet here, is basically we're starting off at 190 nanometers, the lowest wavelength in the deep UV, and we're going up to 20 microns. Again, we're having the possibilities to pump the system with 1030 nanometers, with titanium sapphires, and with 515 nanometers. So going a bit more into details of these light sources, I would start to do with the infrared pumped Levante IR. And I will focus here on the femtosecond version. There is a picosecond version available too, but I think the more popular version is the femtosecond range here. So we are getting typically out 150 femtosecond with a bandwidth pretty constant over the whole tuning range with 100 wave numbers. So the tuning range of the OPO itself is 1300 nanometers to 4850 nanometers. That's signal and idler. And if this tuning range is not enough, then we can optionally extend with a different frequency generation going up to 20 microns with second and third or fourth harmonic generation, basically gapless going down to 330 nanometers. So this is typically 80 megahertz standard, and above 1 megahertz, we are typically shot noise limited. So it's very, very low noise. Classical applications are nonlinear and time-resolved spectroscopy, multiphoton microscopy, and scattering SNOM, which is a kind of near-field optical microscopy, which there typically different frequency generation comes into play, but also the other wavelengths can be used for SNOM. So coming from switching from femtosecond to picosecond. With picosecond, we're having several options. So I want to start with the Pico Emerald FT. I just mentioned at the very beginning. This is a platform where the pump laser is already completely integrated into the optic parametric oscillator. So it's a one-box solution. There are no knobs to tune, to tweak. It's all software controlled. And I will talk about that because that's our coherent Raman light source later in more details. But this system already gives you 660 to 2600 nanometer tuning range with a pulse length of 2 picosecond and a bandwidth of 10 wave numbers, constant over the whole wavelength range. This is a one-box titanium sapphire replacement. So you know that you had the Coherent Myra or the Spectraphysics Tsunami, which were basically the workhorse for picosecond sapphire lasers for the last 30 years. Both basically came into age and stopped, production stopped, I think, in the last few years. So OPOs are a very good replacement for them, and I can basically highly recommend that. Also, this Pico Emerald FT is extendable with second, third, fourth harmonic generation. We go down to 190 nanometers, and we even can pump a second OPO with that, a 1 micron pumped OPO to go further in the mid-infrared. So we basically cover from 190 nanometers to 60 microns. So applications are here: metrology, quantum dot research, coherent Raman microscopy, then FLIM, and laser-based APEs. For laser-based APEs, that's where the 190 nanometers come into play. So as deep as we can go with to the deep UV with nonlinear optics, that's 190 nanometers. Coming to more flexible systems in the picosecond range. These are all green pumped OPOs, such as the Pico Emerald FT, but they are multi-box systems. But we have them in many different power levels and also, most important, many different pulse length regimes. So we can have that for 2 picosecond, for 7 picosecond and 12 picosecond. That is the equivalent of 10 wave numbers, 3 wave numbers, or 1.5 wave numbers. So really narrow band being flexible here. Again, this is fully automated picosecond sapphire replacement, very modular setup. And well, systems can be built from 190 nanometers to 2.6 microns. So 80 megahertz here is the standard repetition rate. If you need something else, please talk to us. Applications are similar to the one box Pico Emerald FT. So metrology, quantum dot research, coherent Raman, fluorescence lifetime, and laser-based APEs. So, and if flexibility is not, if that is not still flexible enough for you, we can build even more systems. So say you want to be flexible with the pulse repetition rate. We can offer pulse pickers, basically reducing 80 megahertz down to, well, 40 megahertz to single shot, basically every repetition rate you like. If the bandwidth, even of a 12 picosecond or Emerald is not narrow enough, we offer spectral slicers, or if you want to have from a femtosecond to picosecond conversion, basically. So we are basically narrowing the spectrum down to, well, 0.17 wave numbers, 0.02 milli-electron volts, which is, well, wavelength is always a bit difficult. So that's an example, 0.04 nanometers at 1550 nanometers. So here, this main market is certainly quantum dot research. That's where most of the pulse slices are actually, spectral slices actually going to. So this is the part for the tunable, general tunable light sources, and then I want to switch gears to coherent Raman imaging. So coherent Raman imaging, first of all, I want to thank all the contributors. Well, we had this new Pico Emerald T launched last year, and we had many contributors from all over the world. I just want to mention Institut Fresnel in Marseille, Columbia University with Wei Min, the IF Nano in Göttingen, KTH in Sweden. We were working with 2 microscope companies together with Leica Microsystems and LightCore Technologies. So they all helped us to qualify the system and to improve it so that we know the quality is good and approved. So Raman, well, talking to the home of Raman. So Raman scattering is a very inefficient process, as you know, but it gives you the full Raman spectrum, which is great. So there is no other way of getting the full Raman spectrum this fast, but still, if you want to do imaging, imaging is kind of painful. That takes very long time. So we have to think of something else to do imaging. And even though there is, well, of course, you have Raman microscopes. They do exist, but you need a lot of time. So to speed that up, people came up with an idea which is called coherent Raman imaging, and I want to focus here on stimulated Raman scattering. So what is basically stimulated Raman scattering doing? We're having on the left-hand side the scheme for the classical Raman process. We are kind of exciting a virtual state, and from there the light is inelastically scattered to excite a vibrational band. Again, that is very inefficient, but we can enhance that. We can stimulate that effect by not only having a laser just shooting electrons into a virtual state, but we can also have, if we have a pump laser and a Stokes laser, which basically stimulates the process directly to the vibrational field, the vibrational level, that can actually enhance the process by a factor, by several order of magnitude. And this is then 3 to 5 orders of magnitude faster than standard coherent Raman, standard Raman imaging. The beauty of it is also to do that, we need short pulses, femto or picosecond pulses. And so we have a 2-photon process, which is only happening in the focus. And that gives you intrinsic three-dimensional 3D capacities, such as second harmonic or 2-photon fluorescence imaging. And this is, I think, something very beautiful. So going a bit more detail how stimulated Raman imaging works. As already mentioned, we are having pulses, femtosecond or picosecond pulses. So think of a 40 megahertz pulse train, and we're having the pump pulse and the Stokes pulse. Typically what we do, we are tuning the pump pulse and we are modulating the Stokes pulse. Why do we modulate? Because, well, what you basically do is we are exciting, we get an energy transfer from the pump to the Stokes if there's a vibrational level. If we switch off the Stokes, then there is we stop the energy transfer. Then we only have the very low Raman scattering. And only when it's switched on, this energy transfer is taking place. And that's what we call stimulated Raman loss. And so the energy transfer still is relatively low. So that is an intensity change in the order of 10 to minus 4 to 10 to minus 8. Very, very low. So how to detect that? Only chance is I modulate, switch on the Stokes, switch off the Stokes, and basically get a modulation, intensity modulation on the pump beam. And that's what I can detect with lock-in detection. But of course, well, what is necessary here to have a very sensitive lock-in detector, and my laser should be short noise limited. Otherwise, the laser noise will overwhelm my actual signal. So laser requirements, I already mentioned that. We need 2 colors, and at least one of them needs to be tunable to excite a different vibrational band. Typical vibrational line width of biological samples are in the order of 10 wave numbers, which translates to 2 picoseconds. So you don't want to be much longer than that, because the coherent Raman process is proportional to, inverse proportional to the pulse length. So shorter pulses are better. But when you're going to femtosecond pulses, due to the time bandwidth relation, you're getting larger bandwidth, and you're losing the spectral resolution. So you want to have 10 wave numbers, spectral resolution, so you're ending up with picoseconds. That is what we at least are convinced is the best way to go. So we are also using laser plus optic parametric oscillators, because that is intrinsically jitter-free and easy to use. It gives you high output power due to efficient parametric process, and it has a very, very low noise. Ideally, it should be short noise limited, and I show you that our systems are. Okay, Coherent Raman Microscopy is already 27 years old. So the first paper came out for Cars microscopy in 1999. And already 5 years later, they switched from synchronously pumped, electronically synchronized titanium sapphire lasers to synchronously pumped OPOs, because then the jitter effect was gone. And so APE already delivered a synchronously pumped OPO for Cars microscopy to Harvard University. And actually, I was the guy who was developing and installing the system at the time. So I'm still pretty proud about that. So this is already, well, 22 years ago. And yeah, I'm still in the field. So it is an exciting field, I can tell you. So several iterations later, from the first Cars OPO, I don't want to use that system anymore. So that was kind of a challenge, but they managed, and that was very stable. But still, that's not what people expect nowadays. So we already had a 2 picosecond system in 2015, one box, but now I will just present the Pico Emerald FT and also the advantages of it. So, Coherent Raman microscopy, SAS microscopy, is not single molecule sensitive, such as fluorescence, but it is still, so you have other advantages. It is label free, which is the main advantages for many, many applications. So you can really just, but you want to push sensitivity. So you want to go down with a concentration, for instance, looking at drug distribution. You want to go into the fingerprint region and not only image CH2, CH3. The CH band typically is a factor of 10 stronger than all the other lines and much easier to image. So the other areas are the areas of interest where many interesting things are happening. And of course, well, there are Raman labels which are difficult to detect. With the old system we had, that was already possible, but there's always room for improvement. So with the old picoemerald S, it took something like, well, 1 to 2 minutes to go from one wavelength to another. So we really want to go to fast tuning, and we also want to increase the sensitivity. So this is basically what we achieved and the comparison between the old and the new one. And I would say that even the old one was already the best in class what you can get in the market regarding sensitivity and reliability. But as already mentioned, the tuning was very slow. So we just are now at a time range of about 1.5 second random axis, wavelength axis. When you just go step by step, then you're in the range from about 1 second or less. That is basically up to 100 times faster tuning. We reduced the repetition rate from 80 to 40 megahertz, which gives you 2 times higher SAS signal or 4 times higher cast signal. We are now modulating exactly at 1/2 of the laser repetition rate, which basically due to heterodyne effects, we increase the signal to noise ratio by 3 dB. Pulse length is slightly shorter than it was before. We're still having the 10 wave numbers bandwidth. The system is short noise limited, and the tuning range we increased again. Now it is basically from 660 nanometers to 1010 nanometers, which basically covers the full Raman spectrum down to 210 wave numbers. So, and what we hope for that is basically, well, we show that is 100 times faster tuning. And I want to show you, in theory, it should give us an improvement of 10 times faster imaging. And that I will show you later. So performance data. Of course, while you need only a few tenths of milliwatts on the sample side. Some people I know that they're using even something like 100, 200 milliwatts. But whatever, your microscope may be lossy, you want to shape the pulse, whatever. So having excess power is always good. So, and we are delivering basically more than 500 milliwatts over the interesting wavelength range, and that basically gives you enough headroom for whatever you want to do in your experiment. Also, what I mentioned, very important, we are looking at in SAS and very small changes in the order of 10 to minus 5, 10 to minus 6. And you only can detect that if your laser source is short noise limited. As I already mentioned, we are modulating at 20 megahertz, so you're detecting at 20 megahertz. So you can see that we are having clearly short noise limited operation at 20 megahertz. So that should be given. So the system itself comes with an easy to use graphical user interface, but you don't need to use that. You can basically use TCP/IP interface for easy integration into your microscope. You can control the power levels for pump and stokes. You can delay the pump and stokes in respect to each other for dispersion compensation of your microscope. Well, the pulses are basically, pump and stokes are already leaving the system overlapping in time and space. And this is also a very important feature, that it works like, well, take a femtosecond TISAF laser. It's pretty similar, and you can start doing SAS with it. You don't need to overlap the pulses yourself. That's all done in the system, and you've got full control of that. So, Raman spectra and SAS spectra. In theory, they should be the same. So, but in practice, it's actually quite not that simple to do, because what you need to achieve for that is that the spectral bandwidth of your laser and the pulse length and the shouldn't change further. The temporal and spatial overlap shouldn't change over the tuning range. No pointing whatsoever. So you need to have a very stable system over the tuning range with as little changes as possible. So what we basically did is, well, that was done in at Columbia University at the lab for Wei Min. They took standard DMSO, just measured the Raman spectrum. It's a bit noisy, I have to admit. And then basically overlaid it with the SAS spectrum. The only thing what they did is to overlap them, is basically taking off the background from the Raman spectrum and basically linearly rescaled it, and you see the features basically are pretty clear to be seen. The peaks are at the same position. The peak height is the same, and even the spectral bandwidth is pretty well reproduced. So we really can say what we get out is Raman-like spectra. So I mentioned earlier that we had that we were expecting 10 times faster tuning. So how do we do that? So we really, in Göttingen at the IF Nano, we just had both the old and the new Pico Emerald, the Pico Emerald S with 80 megahertz and the Pico Emerald FT side by side, sending them into a microscope, and then we were imaging onions. Just very simple. We started off with the CH2 band at 2870 wave numbers, imaged it with 2 microsecond pixel integration time, and then increase the pixel integration to 20 microseconds. So basically 10 times longer imaging time. So then we used the new system, the Pico Emerald FT. And we can clearly see that the signal to noise on the 20 microsecond with the Pico Emerald S is equivalent to the 40 microsecond 40 megahertz Pico Emerald FT. So with 10 times faster imaging, same signal to noise. And of course, when we're going to 20 microsecond with the new system, then of course the signal to noise is improving again. So really 10 times faster imaging. Well, this was now at CH2, the largest band around. So we switched the imaging deep into the fingerprint range to 880 nanometers. And here we have now the Pico Emerald S with 2 microseconds, the old version. You see, oh, that's kind of difficult to see any details here with 2 microseconds. That is certainly not the range you want to work at. So you really have to go at least to 20 microsecond pixel integration time. In comparison, again, the Pico Emerald FT, you can do fast imaging, even in the fingerprint region at small at small bands. And yeah, again, factor of 10 clearly to be seen. And when you go to 20 microsecond, it goes, signal to noise goes up again. It's just only a zoom in just to visually see that we have that factor of 10 imaging. And 2 microseconds, actually, if you have a 1,000 by 1,000 image, 1,000 by 1,000 pixel image, then you have basically with 2 microsecond pixel integration time, it takes it 2 seconds for an image. And I want to show you a small video on how fast actually imaging is working now. This is 1000 by 1000 pixel. And here we first image CH2. We switch then to 1650 nanometers. That is amide 1. And then 1.5 second tuning again, going to CH3 to image proteins. So you really can see within this short time, you're taking a frame, switching to the next wave numbers, taking another frame. So that is zack, zack, zack. So it's easy to access different wavelengths, to acquire spectra and images very quick. So this is the video once again. Just this is real time. I think I really like that video. Especially when you know the old systems, and when you look at the competition, they are much, much faster than anyone else. Here's a nice example by Leica. As I already mentioned, Leica is one of the microscope integrators using the Pico Emerald FT. So this is a Drosophila embryo, and basically time lapse over 45 minutes. You see the cells, the cell is happy, so nothing happens. They're not damaged. It's basically switching between proteins and lipids here, and at the same time also measuring second harmonic and two-photon fluorescence, and basically overlaying that. So gentle imaging without destroying cells is possible. I mentioned 3D capability because, well, it's a two-photon process. And yeah, that's basically a hatched Drosophila larva. And you can see that is 3D capability as expected. It is there. It does work. And talking about spectroscopic imaging, so taking the full spectrum are possible. Again, that was done on a Drosophila larva, basically taking one image at each wave number, and then you have a huge wave number stack, and then you can basically choose a region of interest, and in each of these points of the image, you can then look at the spectra you're just getting out there. And that is something which was previously kind of difficult. And you see, even in the fingerprint region, the very good signal to noise ratio for just only for the spectra and also for the image itself. Another very important application, which has become very popular for coherent Raman imaging, for SAS imaging, is stimulated Raman histology. Why stimulated Raman histology? A histology image, typically classical way, requires a long staining process, which takes you 1 to 2 days. And well, just think of a cancer tumor treatment, well, just kind of, you're in the operation theater and the doctor needs to decide whether he's finished or not. How should you know? So they basically take the samples, they just look at it doing the staining process. That takes, well, 1 to 2 days. They can't keep a patient open. So you basically have to finish your surgery, have to do the test, and when you realize you haven't cut everything, you have to restart the process. So to simplify that, to speed that up, the stimulated Raman histology is one of the possibilities, basically, to have that system, such a microscope in the operation theater, and basically take your sample slice, just look at it. That is a process which takes minutes instead of days, and you can see whether that is cancer or not, to conclude with the surgery or not. So that is, so many companies are working on that, and you see with the Pico Emerald FT, that is easily done, best quality. You can imagine light core technologies even just developed a virtual, basically deep learning algorithm to do the coloring. So surgeons can't tell the difference between the classical staining and this method. So just other example of imaging. Again, this time this is plant imaging. So we are basically scanning through the amide-1 band, and you can see at different areas there are different chemical compositions, and therefore they're lighting up at different wave numbers. So, but I think the most difficult part for coherent Raman imaging is, well, when it comes to labels. Why should we label? Previously, I just said, well, it's so great that coherent Raman doesn't need, well, Raman microscopy doesn't need labeling, but there are certain areas where you would like to label. And there's this Raman silent region, basically between 1,000 and 2,000, 2,500 wave numbers. And one of these Raman labels is basically alkynes. These are these carbon triple bonds, which give a distinct peak in the area of 2,100 wave numbers. Wei Min and his team basically pioneered the whole field of Raman labels, but they're difficult to detect. So we just wanted to see whether that works. And yeah, he just got that working. So you see the image of HeLa cells here, which were incubated in 100 micromolar of EDU. It's clear, very nice images we could get there. And they really pushed the sensitivity, and they then even tried to do that with, they incubated the cells in 10 micromolar EDU. They were still able, I mean, okay, it's getting noisier, but they still were able to detect that, and they were never able to do that before. And yeah, with that, I want to conclude with the examples I showed you. So just want to give you the microscope options for the picoemerald. So many people just build their SAS microscope themselves. So basically every laser scanning microscope can be used. Olympus, Nikon, Zeiss, Thor Labs, you name it. Basically all they work, as long as they have, you have the proper objectives and condensers for that. You have the, you need a good detector. You can either build it yourself, or you just can buy them commercially. So here's a link for a company who does it. But you also, if you don't want to build yourself the system yourself, you can fully integrate that with the Leica Stellaris microscope or the Bond Explorer microscope for Lightcore Technologies. And with that, I want to conclude. The picoemerald is our newest coherent Raman light source. It has 100 times faster tuning, 10 times faster imaging. It's really two-shot noise limited, which is very, very important. No balance detection needed. It gives you real Raman spectra, fast and easy spectral scans. And you can image CH, fingerprint, Raman tags. It's all in there. And well, I think this is what I wanted to tell you today. I thank you very much for joining me, and I'm open for questions.
Okay, thank you, Dr. Rimke, for this wonderful talk. So, as we already requested to our audience that if you have any questions, please put up in the chat box there. We have some of you received here, so we will take them one by one. And let me go to the first one. So it is from Pritam Shetty, Mr. Pritam Shetty. So how do you measure dispersion from microscope to compensate objective? I think this is that.
Yeah, this is a standard procedure where you already mentioned it correctly. Every objective is slightly different, has a different dispersion. So that you have if you have a Stokes beam at 1030 and the pump beam, say, if you want to do CH imaging, then you're working at around 800 nanometers and 1030 nanometers. Typical delay between 1030 and 800 nanometers is something like 2 picoseconds. So what you need to calibrate it, you just either do coherent Raman or you do second harmonic on any kind of sample, and then you go to different wavelengths. You have the possibility to scan the delay, you find the optimum, and basically put that down. You do that basically every 50 nanometers to find the temporal overlap. That's basically by scanning the delay, looking at the intensity of your signal, second harmonic or a coherent Raman signal, and well, then you calibrate. You have a curve. Then you do a second or third order fit, and basically with every command you have wavelength command, you send then the delay command to the system. That's basically it.
Okay, thank you. Hope that that has answer for the question. So we have another one from Mr. Sudhir Dikshit. I think they are asking for the requirements on setting up such a femtosecond tunable laser sources, like what type of technical requirements or the utilities are required, like class of clean room, possible lab size, temperature control, humidity control. So that are the questions which they have asked it here. So
so environmental conditions are, well, we very strongly recommend a optical table to set it up with. It should be in a climatized room with temperature stability of ±1 degree, and humidity should be below 60%. So clean room is not required. So basically standard, well, you need good lab conditions, but that also is for the microscope itself. They don't like it when the temperature changes too much. In theory, even with stronger temperature variations, it does work because there is an active cooling in it, in the system, but we recommend to have it as stable as possible.
Okay, thank you. I think all the technical requirements or the utilities come with the system itself once it is delivered. Yeah. And then there is a question from Mr. Anubhav. Are these images correspond to Raman mapping? I think slide 35, 37 he is referring to image. Does these images correspond to Raman mapping? So that's what they mean to say.
Well, I showed the spectrum, the basic spectral comparison on DMSO. Yes, the spectra are the same.
Okay, thank you. And then one question is Mr. Boomer D. Pujit. So the question is that what is the advantage of image mapping using pulsed laser source? Is it only to keep biological samples safe from laser burning? How is it comparable with continuous laser Raman mapping images in terms of accuracy or edge?
CW lasers, well, you use CW lasers for classical Raman scattering, spectroscopy or microscopy. But here we are talking about a 2-photon process. For 2-photon process, you need peak power. Otherwise, it doesn't happen. So you need pulses. With CW, coherent Raman doesn't work. It's basically the question. So it's the same thing when you want to do 2-photon fluorescence. You can't do 2-photon fluorescence or second harmonic imaging with CW lasers. So it's basically the same argument.
Okay. So this relate to the realization time between the vibrational states of the transitions. Is there any role of that? So I'm just want to understand that the difference between CW and the pulse. So do you mean, so is there any role of the relaxation times that means between different energy levels?
No, relaxation times don't play a role here at all. So if you think of the pulses are separated by 25, so we are working at 40 megahertz. So it's 25 nanoseconds between the pulses. And so that is comparatively low. And also the amount of So you don't have any accumulation of Raman states. So there is enough time between the pulses.
Thank you. And there are two last questions because we are already running out of time. So does this technique work with samples which are fluorescent?
Yes, it does. Because fluorescence, first of all, is redshifted. So, and we are just looking at the pump. So we're detecting the pump, not the Stokes. So it's actually separated by wavelength. And yeah, fluorescent samples are possible. Plants are typically more difficult because they are fluoresce more, but I've shown you plant imaging. So it does work, yes.
Okay, thank you. Thank you for your answer. So can the autocorrelator be used in case of studying for 20 nanometer light and exciting 778 nanometer field in case of rubidium?
I have to admit, I don't completely understand the question. So well, what do you want to use well, you can use an autocorrelator to measure 420 nanometers. That's not a question. And so I don't see the
so we would request,
sorry for that.
We request Mr. Amri that please write a question here and or share it in email so that we can get back to him with the answer from your side.
That would be great. Yes.
I think, yeah, that will be perfect to get better response. So at the end, I would like to thank you, Dr. Rimke, for sharing your valuable knowledge and insights with us today. We also extend our sincere thanks to all our participants for their active participation and thoughtful questions which were here today. We hope today's session has provided valuable insights into light sources for coherent Raman microscopy, multiphoton microscopy, and ultrafast spectroscopy. Thank you once again, everyone, for joining us at LaserTalk 25. We look forward to welcoming you to our next edition of LaserTalk webinar series. At the end, I would like to thank personally to Dr. Rimke for his wonderful and exciting talk with detailed discussions on various applications. And we expect to host you in future as well. And looking forward to see you again.
And thank you very much from my side to everyone watching us. And yeah, thank you. Have a nice afternoon.
Yeah, thank you, everyone. Thank you, Rimke. Dr. Rimke, thank you. So let's conclude it.
Okay.